today's lesson is on piecewise functions. A piecewise function is a function that is defined by more than one equation, and each of those equations has its own limited domain. Now, part of this lesson, we're going to look at graphing piecewise functions. So now that we've been introduced to the library of functions, we'll at least have an idea of what these pieces should look like. Our most common piecewise function is actually the absolute value of x. A lot of us don't think of it as two different equations put together, but it is. The absolute value of x is defined by positive x if x is greater than or equal to 0, and negative x if x is less than 0. So I can quickly sketch what this looks like. X is a linear equation with a slope of 1, but that only happens for x values greater than or equal to 0, so that's like this piece right here. There's my slope of 1 for x values greater than or equal to 0. Negative x is a linear equation with a slope of negative 1, but that's only true for values less than 0, which is going to yield the other part of our v that we know makes up the graph for absolute value. So first, before we graph, let's just practice evaluating a piecewise function. So we have f of x equals negative 3x if x is less than negative 1, 0 if x is equal to negative 1, and 2x squared plus 1 if x is greater than negative 1. These right here give the domains of their respective equations. So the first part asks to find f of 0. We have to determine which of those equations we're going to use for f of 0, and that's based on these domains here. So where does 0 lie in these domains? Is 0 less than negative 1? Is 0 equal to negative 1? Or is 0 greater than negative 1? Since 0 is greater than negative 1, we are going to use the third equation. And just like before, function notation just simply means take 0, plug it in for x. So this is 2 times 0 squared plus 1, which simplifies to 1. And we know that function notation and evaluating a function like this generates an ordered pair. So there's actually an ordered pair on this equation at 0, 1. And this is an ordered pair for my entire function as well. Next, we'll find f of negative 2. Again, we need to identify which equation we're going to use in order to evaluate that. Are we going to use this first equation? Or are we going to use the second equation? Or are we going to use the third equation? Since negative 2 is less than negative 1, we are using the first equation. Negative 3 times negative 2 is 6. So another point on our function is going to be negative 2, 6. F of negative 1. Looking at our individual domains here, when x equals negative 1, we use the equation y equals 0. So this is the second equation. And since we don't have an x to plug in, we know that the y value is just going to be 0, generating a third point on this function, negative 1, 0. Now these are just 3 points for our function. On the next example, we're going to look at how to actually graph it, so we'll have infinitely many points. To graph a piecewise function, there are 2 more common techniques. I'm going to show you guys both with the same example. So f of x equals x minus 1 if x is less than 0, and x squared if x is greater than or equal to 0. The first technique involves making a table of values for each of our equations. So we're going to make a table of values for y equals x minus 1, and another table of values for y equals x squared. And we're going to use these domains to determine what values of x we're going to plug in. Now we're always going to use the endpoints of our domains. If I think about this as an interval, x is less than 0, is negative infinity to 0. X is greater than or equal to 0 is 0 to positive infinity. So we always want to plug in our endpoints. So for both of these, I'm going to plug in x equals 0. For the first one, y equals x minus 1, we also have to pick another point that's in this interval. Since it goes all the way to negative infinity, we don't have an endpoint down there, so we'll just pick any other point in the interval. So let's try negative 3. When we plug in x equals 0, 0 minus 1 is negative 1. When we plug in x equals negative 3 minus 1 is negative 4. Now what we want to pay attention to is that we can't include 0 here, right? This is strictly less than 0. So is this actually going to be a point on the graph? And the answer is no. This is going to be a hole. And that looks exactly like what you think. We're going to draw a point that looks like a hole. So at 0, negative 1, there's my hole. And then I have a point at negative 3, negative 4. And connecting these two and continuing towards x equals negative infinity, we have that linear piece. Now, for our second table, we chose x equals 0, which is one of our endpoints. And since our other endpoint is infinity, we'll just choose another value that's in that interval. So let's try x equals 3. When I plug in x equals 0, we get 0. When I plug in x equals 3, we get 9. And actually, I'm going to try 2 because it looks like on my graph only goes up to y equals 5. When I plug in x equals 2, we get y equals 4. If I look at this domain a little bit more closely, I can plug in x equals 0. So this point 0, 0 is not going to be a hole. It's going to be just a regular point. So we have a point at 0, 0, a point at 2, 4, and we actually, if we think about x squared, we know we've got a point at 1, 1 as well. And x squared is a parabola, so we have that joined with that nice half parabolic shape. And that's using the knowledge of that parent function y equals x squared. We know what it's supposed to look like. So even if I had not plotted that point 1, 1, I know that I'm not going to connect those 2 points with a straight line because I know what the graph is supposed to look like. So that's one way of graphing a piecewise function, and that's making 2 tables of values, or 3 if there are 3 different equations. But you're representing each equation with its own table of values, making sure that you use the endpoints of their domains. Now, the other option is to graph each equation and then focus or erase part of the graph that you don't need. So in red, I'm going to graph the equation y equals x minus 1. The y-intercept is negative 1. The slope is positive 1, so I'm going up 1 over 1, up 1 over 1, or down 1 to the left 1. So when I connect these points, I get a straight line. Now I want to pay attention to the domain of this. This is for x values less than 0. So I only need stuff to the left of the y-axis. So I'm going to go in here and I'm going to erase everything that I didn't need. Now I also actually need to erase that one point right there. You see it going away? But we get really close to that, so we want to go back and add our hole to indicate that we do get really close to that ordered pair, to that point 0, negative 1, but we don't actually get there. Now in yellow, I'm going to do the same thing for my second equation, y equals x squared. Those landmark points from our library of functions that we just learned about, negative 2, 4, negative 1, 1, 0, 0, 1, 1, 2, 4. Again, I got those points by just plugging in the x values negative 2, negative 1, 0, 1, and 2 into x squared. And when I graph this, we know that it's our parabola that looks like this. And now, paying attention to the domain for this one piece, it's for x values greater than or equal to 0. So I'm going to go in and erase the part of the graph that I don't need. This is only true for x values to the right of my y-axis, so I'm going to erase everything to the left. But since it is true of 0, I'm going to leave that point there at 0, 0. So you can see that we got the exact same graph. It's just two different ways of getting to that answer. You guys can choose whatever method works best for you. So I've replicated the graph here. It's kind of on my head, but you guys can see it. Let's try to find the domain of this function, okay? Now, it's a little trickier because now we see that we've got two different pieces, don't we? But what x values do we have y values for? We know we've got everything until 0. That's where this line ends. Do we include 0 here? The answer is no, but look what happens. We immediately jump up to this piece. So we could take these two pieces and basically bring them together and it would connect perfectly, wouldn't it? Making a smooth, continuous line. So the domain of this function is actually negative infinity all the way to positive infinity, even though we have two separate pieces. And if we look back, I know it's covered by some writing right now, but looking at the domain of the two individual pieces, x values less than 0, x values greater than or equal to 0, are there any gaps between the two? And there isn't. So that's what indicates also that our domain is negative infinity to positive infinity. Now we think about the range. The range is our y values, right? So we're looking at this vertical axis here, and we can see pretty clearly this elephant in the room, this huge gap right there. And that's going to be a gap in our range. So what's the range of just this piece down here? Well, it goes all the way to negative infinity, from negative infinity, and it stops at y equals -1. So that's going to be our first interval, negative infinity to -1. And because we have that hole there, we're going to have a parenthesis on our range. Now we leap up here to this next piece, and the y value, this starts at 0. And we can see that it climbs all the way up to positive infinity. Do we include 0 in this interval? Since we actually have a point here, we do. What about the intercepts, the x or the y intercepts? Well, be very careful. A lot of us have a tendency to look at this hole down here and think of it as a y-intercept. But again, that hole just says we get really, really, really close to that point, but we're not actually there. And since we're using a pencil or a pen, we can't physically draw that and show that we're getting infinitely close to that point, but not on that point. So that's why we use the hole. So this is not a y-intercept, but we do have this point right here at 0, 0, which is both an x-intercept and a y-intercept. And then we talk about whether or not this function is continuous. Now, I mentioned this word earlier, but what do we think continuous means? I had a teacher back in high school who, when she was describing continuity to us, asked us whether or not we could draw this picture, draw this graph, without picking up our pencil. If we can draw it without picking up our pencil, then it is continuous. If you have to pick up your pencil to draw the graph, then it is not continuous. This graph is not continuous. So now let's look at an application of a piecewise function. Many of you have probably had a piecewise function involved in some type of billing that you've you've had, whether it's a cell phone, or in this case, we're going to look at a gas bill, which I know in Florida we don't typically use gas, but maybe some homes still do, some older homes, more common up north. So we have this printout from some company, some gas company, People's Energy. In April of 2009, People's Energy had the following rate schedule for its natural gas usage in single-family residences. So they tell us that the monthly service charge is $15.95. The per therm service charge, the therm is an individual unit of natural gas. The first 50 therms are about 34 cents per therm, and then any therm over 50 is at a discounted rate of about 11 cents per therm. And then you also have a gas charge of about 40 cents per therm, but we're going to use these actual decimals. And we've seen this. If we think about our cell phones, now they're a little bit more simplified now, our cell phone plans. Pretty much everyone's on unlimited everything. But if you recall, maybe about 10 years ago, you were paying per minute, per text message. So when you bought a certain chunk of text messages, you might have paid one price, but then as you bought more, you got a discount on them. And that's what we're seeing represented here, with the first 50 therms costing more than the therms over 50. So I want to know, what is the charge for using 50 therms in 1 month? So I know this is small, but this is just relaying that same rate schedule that we had on the first page. And we have to think about what goes into our bill every month. Well, we know we're going to have our monthly service charge. So we've got $15.95 just for being a member, just for having them provide service. Now we have to pay for our per therm service charge. Since we use 50 therms, are we in the first or the second category? Well, the first 50 therms, which is what we've used, are 33,606 cents per therm. So we've got 0.33606, and we've used 50 of them. And last, we have our gas charge. Our gas charge doesn't change based on how many therms we use. It's constant. So we also have another 0.3940 times 50. So go ahead and pause the video here for a second and calculate this using your calculator, and then press play and we'll go over that answer. When you multiply and sum these values, we get a bill of $52.45. That's if we used exactly 50 therms in 1 month. What if we used 500 therms in 1 month? How does that change the way we determine what our bill's going to be? So again, we have our service charge of $15.95. We also have a per therm service charge. Now here's where we've got to read very carefully. The first 50 therms are 34 cents per therm, about. And then the therms over 50 are about 11 cents per therm. Are we going to get charged this 34 cents for the first 50 therms no matter what? What do you think? Well, I can tell you that this People's Energy is out to make some money. So if they can charge you the more expensive rate at the beginning, they're going to. So we've got 50 therms charged at 34 cents per therm. So we've got this 33606 times our first 50 therms. And then the rest are what we're going to get discounted. So how many do we have left that we're going to multiply by this 11 cent rate? Well, if I've already paid for 50 therms and I used 500, there are 450 therms remaining. And then we still have to consider our gas charge, which, remember, the gas charge is not dependent on the number of therms, so it doesn't change. So we're going to pay the same 39 cents for all 500 of those therms. Again, go ahead and press pause here. Type this into your calculator and see what your answer is. Come back in a second and we'll confer our answers. For using 500 therms in 1 month, our bill is $277.36. Now, we've gone through quite a bit of work just to determine our bill, right? And depending on the number of therms, we changed how we figured out what our bill was going to be at the end of the month. So what we can do is take this information, take this process that we use to determine the cost, and write a function for any number of therms. Since we have two different scenarios, whether we use 50 therms or less or more than 50 therms, we actually have two equations, so we will generate a piecewise function. So we want to develop a piecewise model. Remember, writing a model is just like setting up an equation or writing a function for something that relates your charge, C, for x therms of gas, excuse me. So let's look back at the steps we just took. We know that we've got two cases. We've got when our gas usage is less than or equal to 50 therms. Remember, that's the case where we use the first 50 therms. And then when we have more than 50 therms. This column, we're going to be looking at example A. What did we do to determine our bill when we had exactly 50 therms? Now, we're going to consider it as X, so we want to figure out exactly how to determine the cost for any number of therms. So we're using a variable here. Well, we know we had the $15.95. And then we had our per therm service charge, which we took each therm. When we had 50, we multiplied all of our therms by that, 33,606? We multiplied that by X. And then we also had our gas charge. Our gas charge was the 39 cents. And we multiplied that by our 50 therms. So this was our service charge. This is our per therm charge. And this is our gas charge. Now we can combine these like terms. When we do so, we get 15.95 plus 73006. Excuse me, 73006. X. This one was pretty straightforward. I think we probably agree that evaluating the bill when we had 50 therms was easier than when we had 500. So this is what we did for the first one. And now let's consider how we figured out our bill when we had more than 50 therms. Well, we started out with our gas charge, or excuse me, our service charge, which is a constant, $15.95. That's not dependent on the number of therms we use. We could not use any gas and still have a bill of $15.95. Then we got into the per therm charge. If you recall, we spent the 34 cents for the first 50 therms in that Part B setup. So we've got that 0.33606 times 50. And then the remaining is what we multiplied by that reduced cost, the 0.10580. Now, how many therms did we multiply by that 11 cent charge? Well, in the example B, we used 450. But think about it, we had actually used in that month 500. So we had taken our total number of therms and subtracted the original 50, which we were charged at that higher rate. And then we have our gas charge, which doesn't depend on the number of therms, so we just multiply it by each therm used. So now we need to combine all these like terms. We're going to have to distribute here. So let me show you what we have when we distribute. We have 1595 plus, I don't know what this multiplied by is, but 0.33606 times 50 plus 0.10580x. Now I'm distributing that. When I distribute the 0.10580 times negative 50, we get negative 5.29 plus the 0.3940x. So take a second here, go ahead and multiply out this value, and then I want you to combine like terms. Notice we have a like term here and here, and then all of our constants are like terms. So when we combine everything, we get 27.463 plus 0.4998x. So these are the two equations that we use to determine our bill regardless of how many therms we use, just for X number of therms. So let's go ahead and write our cost function. Okay, we're copying down from that previous slide. When our therms were less than or equal to 50, we use the equation 0.73006x plus 1595. When x is greater than 50 therms, we're going to use the equation 0.4998x plus 27.463. And this is actually the computer model that they probably have set up at People's Energy, and they just input data into here so that nobody's actually figuring out by hand exactly how much it's going to cost based on their rate schedule. So maybe a challenge for you guys is to take a look at your cell phone bill. See if you have a rate schedule that's modeled by a piecewise function, and try to evaluate how much your bill would be depending on certain number of minutes or text messages used. And we'll see you next time for our discussion on graphing functions using transformations.